My name is Hongyeon Thai, and I am from ARM, not located in UK, but from Austin, Texas. And today I will talk about ARM64 optimizations in Microsoft Visual Studio 2022. This is quite a big crowd, so hang on tight till you see it. It's going to be a very wide presentation. Let's get started. Here the agenda for today. I will talk a little bit about Windows on ARM, and then talk about ARM64EC, or the emulation compatible. Why do I need to talk about that? I'll mention it, and then I will talk in detail about the optimizations in MSVC from 17.6 to 17.10, and then followed by the current work and the plan for MSVC. And then I will conclude my presentation for today. First of all, Windows on ARM. Why Windows on ARM? Why not, right? You know, everybody, I think everybody have your cell phone, and inside your cell phone, I think it has some ARM chip in there. And everybody loves it, right? You love your cell phone. So why not Windows on ARM PC? It's lightweight. Why is it lightweight? We know already, you know, it has low consumption, power consumption, so it doesn't have fan. Correct me if I'm wrong. The PC doesn't have fan inside, and you can go on your typical day without having to worry that you will run out of battery, because it can last throughout the day. And you know, it also turns on instantly. What I mean by that is that you can press the power button. It's just the screen will go blank, and you go, you know, take a break or something. You come back and press the power button. It just turns on instantly, and it's connected to the internet all the time, as long as you want, because you know, using a cellular data, as long as you have a cellular signal, it's going to be connected to the internet all the time. So what's not to love about Windows on ARM, right? Okay, let's get going for ARM64EC, or the emulation compatible. What is it? The native application perform better on ARM, but to port from existing x64 to ARM64, we have to recompile everything. And not all the app is just a simple main program, right? That have could have a third-party dependencies, or they can have plugins, or even sometimes have the architecture specific, like assembly, which is maybe written in x64. So to port that is kind of challenging. So Microsoft created this called ARM64EC. It makes developer lives easier to port the application from x64 to ARM64. So it guaranteed by Microsoft that it will work seamlessly with x86 binary. So developer can port the critical part one piece at a time. So it can port incrementally until they reach their final goal. Then they can port everything into ARM64. That is the goal for this new ABI. This ABI is not compatible with ARM64 ABI. It at the higher level, Microsoft makes some change a little bit so that it works with x64 binary seamlessly. So I have two tables here. It just the top table just show a linkability. If a user want to create ARM64 executable, it can link with the libraries that built for x64, or the libraries that built with ARM64EC, but it cannot link with the library that built for ARM64 target. On the other hand, if the user want to build ARM64 executable, it can only link with the library that built for ARM64, not with the other two types. Similarly, if you have the process, for either x64 process or ARM64 EC process, it can load either x64 binary or ARM64 EC binary, not ARM64 binary. That's how it gets set up right now. So let's look just a little bit of how developer port from existing x64 to ARM64 EC. First of all, they need Windows 11. ARM64 EC is not available in the previous Windows. In the previous window, I believe it has a different kind of emulation called x64 emulation. But for ARM64 EC, it needs Windows 11, and of course, it needs Visual Studio and ARM64 EC tools. So developer can usually check if they have the tools already installed by open a Visual Studio installer at the top right image here. They can open up the application and see if the ARM64 EC tool is installed or not. And then they can open up the existing application, which is normally it's this particular example, it's in Visual Studio application, and they can add the target ARM64 EC as you can see in the top left, in the bottom left, and on the bottom right image shows that it shows just a simple program. So if you're not familiar with Visual Studio, when develop application, they do it in Visual Studio solution, and in a solution they can have multiple projects. The projects can be libraries, or they can be main program. For this particular example, it's just a simple solution, contains 2 projects. The top one is just a DLL library projects. And if you can see the platform, it's targeting x64 platform. And the bottom project is just a simple main program, and it's targeting ARM64 EC. As you can see, developer can mix and match 2 different targets in the same solution. Now is the fun part. MSVC compiler optimizations. We have been working with Microsoft compiler team for more than a year now, helping them to do some performance improvement, and also adding some feature to the compiler. And I have listed here some of the optimizations that we have done over the past year from 17.6 and 17.10. So I will pick out some of the examples and talk in the next few slides. For the one that I don't mention here, I listed the blogs here. If you're interested, you can go follow the blogs. Microsoft have a schedule that a release schedule every 3 months they will release, and every 3 months we will generally write the blogs about what kind of optimization we do for the compiler. First of all, the auto-vectorizer support for more SIMD instructions with asymmetric operands. What do I mean by asymmetric operands? Here I have example of a very small code. It's just a simple loop, a loop with a for account, and it multiply 2 shorts, 2 array of shorts, array B multiplied by array C, and then add it to array A. As you can see, B and C has a type of short, and A has a type of int. They're not the same size, not the same type. So in order to operate together, we have to promote B and C to be the same size as A. So at the bottom in the table here, we do a comparison between before the optimizations and after the optimizations. So for the left table, the first 2 instructions, what it does basically, it just sign extend short into in size. And then in the third instruction, it multiply two vectors together, and then add to array A. That's basically what it does in the left table. So on the right side, this is after the optimization. ARM has an instruction where it allows the last two operands to multiply together. In this particular example, it's a 16-bit wide size, multiply together, and then widening the result to be the same size as the first operand, and do a multiply and put the result back in the first operand. That is called vector sign multiply accumulate long. So not only it frees up more SIMD register, now it doesn't need to use vector 19 and vector 18. It also reduced the code size from 3 instructions into 1 instruction. The next optimization is by element operation. What do we mean by element operation? So ARM allows some operations. It allows a SIMD register to be multiplied by an element from another SIMD. So let's look at the example here. This is also a loop with a 4 count. So we can do 4 of them at a time using a SIMD instruction. But in this particular case, it multiplies its scalar C into an array B. So on the left-hand side, this is before the optimization. The first instruction is called a dupe. Basically, it just copy the first element 0 from vector 0 into 4 lanes in vector 17, basically doing a duplicate. So we know that we don't have to do that. So in release 17, instead of having to do a duplicate, we can just directly multiply using the element 0 in this particular case, and multiply to vector 17 and put the result back in vector 17. That is the second instruction on the right-hand side. So for this particular case, we also get the better code size, and we also completely eliminate the dupe instruction, which generally take about 2 cycles to run on the system, for example, on the newest system. Now, the next instruction is called move I, move ni, or move immediate into vector, or move ni, which is move inverted immediate into vector register. I have 2 different loops here that show example for each instruction. The top loop will show demonstrate move I. The bottom loop will demonstrate the move ni. So as you can see here, the code size on the left-hand side, this is before the optimizations, and the right-hand side, the code size is cutting in half. And also I think the runtime is also better because the load instruction, which is the third one on the left-hand side, usually takes more cycle to run. So, and yeah, the code size is better and the runtime is better. Next instruction, it's a conditional compare. For this example, we have a good example that can be short circuit. We have 2 comparisons. If the one on the left is true, we don't have to do the right comparison, right? So if you can predict that the code, if you can predict that the A equals 17 is always true, then the branch would be the more preferable because you will only execute 3 instructions, right? But we cannot always predict it unless you use a profile feedback to check if that branch is always taken or not. So, and in 17.8, Microsoft has looking at the cost model, and it has determined that using a conditional compare and conditional select, it still get a more beneficial than just using a compare and branch. The last one that I will talk about the C runtime optimization. This is done in 17.10. For historical reason, Microsoft has split the C runtime library into two parts. The first part is called UCRT, or Universal C Runtime, which contains the standard C library, and it's part of the SDK. The second one is called VC Runtime, which is compiler specific, and it contains certain code that is important for program startup and some other feature like exception handling or some intrinsic. So if you look at the link order, the VC runtime will get linked in first and followed by UCRT. The UCRT is optimized, but not the VC runtime. So we optimize the function like memset, memcopy, and some other runtimes that mentioned here. So how do we do that? Luckily, ARM already has a tuned version of the C library. So what we do is basically we just go and grab from that GitHub link. It's publicly available and it's free. So how good is that for ARM, right? And so we integrate that into VC runtime, and performance is great compared to the older version. And also coming up in 17.11, MSVC also doing more tuning of those C runtime libraries. So you see more of the optimization instead of calling the runtime into the library. We just inline the code, which is better. From the GitHub website that I just mentioned before, it comes with a micro benchmark. So we run that micro benchmark on a memset, on Neoverse N1, on different size of buffer. The blue one represents the ARM tuned version, which is a newer version. The brown bar represents the older version in MSVC. And as you can see, most of the time, it runs almost twice better than the older version, except just a few cases where the buffer size is small, between 8 byte to 32 byte. This is because we think that because the older version of MSVC use a jump table, and a jump table tend to perform better when the buffer size is small. But before we integrate the newer version into MSVC runtime, we run through many benchmarks, both internal and external, and we don't see any performance degradation. So we decided to integrate the ARM version. So for the current plan of the MSVC, you might think that what is going on? Why is MSVC is behind on SVE? You have to think about the hardware. It's just available. It's not the priority. So, but we are now working on it. So SVE assembly, SVE2 support, it's in, and they are working on SVE intrinsic support, and it's going to be done in a few months. SME, SME2 assembly, it's going to be done at about the same time in several months. If not, if we find a hiccup, it's going to be done by the end of the year for sure. And also, we're going to be working on SVE auto-vectorization. I expect that to be done, the basic auto-vectorization is going to be done by the end of the year. So, and for the security feature, MSVC has done a great job already, prevent the ROP attack, and they use a pointer authentication method, and also some control flow graph guard to prevent memory corruption. But they're still missing the job or jump-oriented programming mitigation, and we think BTI will help. BTI is a branch target identification, and the work for BTI, I believe that it's going to be done after SVE auto-vectorization is done, which is likely going to be next year. So conclusions, MSVC is an important part of the Windows on ARM ecosystem because it's being used by internal customers and also external customers. And you know, SVE is important for many customers, so it's coming. So, and Microsoft would like to hear, actually too, we'd like to hear from developer community, and Microsoft has a website where developer can participate and give some feedback or comments, or like to hear, you know, what's important for developer, and they have a website for the developer, and also they have a website for a blog. You can follow what's new with MSVC, right? And for ARM64 EC, like I said, it's very important, you know, to have more applications, more native applications, and ARM64 EC, it's a pathway to get to that, because sometimes, you know, it's not that easy to just port everything all at once. And I think ARM64 EC is the way to go. And we have link on both from Microsoft website and our website. It has great contents, you know, video and how to debug, how to port from x64 to ARM64 EC. And that's it for my presentation today. Thanks for coming. If you have any question, comments, or yeah.
Yeah, I have a question regarding ARM64EC. So, what is the future of ARM64EC architecture in terms of support? For how long it will be alive, or like how do you see that?
It should be alive for some time. So until we get, actually I cannot talk how long it's going to be because I'm not from Microsoft. But I think it's going to be live for some time.
Microsoft person is
oh, you are? I'm sorry.
From what I understand it, it's going to be at least 5 years.
And also, another question related to that, does it make sense to add ARM64 EC API to another toolchain, for instance, to the toolchain?
Well, it would be great if another toolchain, you know, enable this API. So
Qualcomm engineers contributing to LVM.
Yes, they are. Yes. So ARM64 EC support in the LLVM is there and everything.
Okay.
But not well, you guys just started the beginning of it. So that's something that I asked. Is it on your guys' plans, you know, and everything, and it's not on ours currently, but that doesn't mean it won't change. So, yeah.
yes.
This is less of a question, really, but more of an offer. I am the technology manager for all the LLVM and
Yes.
development. As you're getting performance ACLE implementation and SV2 auto-vectorization working.
Yes.
Number one, I'd recommend using the GNU and LLVM compilers to as a demonstration of what performance you can get on it. If you can find a workload that Microsoft cares about and compile both and see maybe where your performance sits against ours. If you do that, and there is a performance difference, please come and talk to us, and we can help. We will almost certainly be able to help you through what the compiler is doing more quickly than you'd be able to do on your own.
Yes.
But this is really good progress.
Yes, definitely. We have a team lead. He also been talking to the compiler team in.
No,
yeah.
I know John.
Yes, John.
I just want to keep reiterating that we obviously can't help with the development itself, but we're more than happy to help with guidance, to help you, because this is really fast progress, but it's a big job to do this.
Definitely.
I think Qualcomm will have the same offer too.
All right, thank you.
As far as I understand, we are talking with you guys, but I don't know the exact details.
Okay, good. Yes.
Are these optimizations also available in MLVM?
Yes, mostly. I mean, exactly which optimizations. Yeah, but it is the case that Neon and SVE auto-factorization code quality is very good in both we use both these toolchains internally to develop the SVE architecture 10 years ago, and so it's pretty easy to do.
All right. Any more? Yes.
You said that there were some changes to intrinsics and that kind of thing coming in MSVC.
Yes.
Is there an intention to make them closer to what you would expect to get from LLVM and GCC? Because it uses things like type def, vector types and things like that, which make porting code difficult.
I don't know the detail of the implementation yet, so there's some people working on that. So, but I will, so I can.
Existing code has to basically be rewritten. So
yes.
Basically
Yes.
the MSVC style rather than
Yes.
any other compiler style, and it makes Windows and ARM porting a hard sell to people that go, oh, but you can't. You're going to have to rewrite all your Neon intrinsics at the same time. Most people just go, nah, maybe not.
Yeah, there's a lot of work to be done. Yes. Okay. Thank you very much for coming.